Shall we start? Sir, shall we start, sir?
Yes. We can start.
Okay.
What about our resource person?
Yeah, she's here. Susan.
Okay, fine.
I'm here.
Okay.
Susan Jacobs. In the name of Susan Jacobs. She's here. Bincy, are you here?
Yes, I'm here. Can you hear me?
Yes, we can hear. Okay, we shall start. Good afternoon, everyone. It gives me great pleasure to extend a warm welcome on behalf of Department of Physics, St. Aloysius College, Edatwa, to this webinar on physical properties of chromium, rhenium, vanadium alloy system by a resource person, Dr. Bincy Susan Jacobs. She is a lecturer at the University of Johannesburg, South Africa. She completed her undergraduate and postgraduate programs in physics from the University of Kerala, Thiruvananthapuram. She did her PhD from the University of Johannesburg. She received various NRF grants during her PhD and post-PhD track. She was awarded the most outstanding presenter at the annual SAPE conference. She has many national and international publications to her credit. I welcome you, Dr. Bincy Susan Jacob, to this webinar. I also welcome our principal, Dr. Joseph, for his continuous support, without which the webinar couldn't be possible. We welcome you, sir. I also welcome our HOD, Ms. Rospin John, my colleagues, and all the participants to this webinar. Now, a note of instructions. I'm Rani George, coordinator of this webinar. Participants are requested to mute their audio and video during presentation. If you need it to post any comments, utilize the chat box. Doubts and questions about the session will be addressed at the end of session. Link to the feedback form will be posted towards the end of session in the chat box of both the Google Meet and the YouTube link. Certificates will be issued only to those participants who fill the feedback form. Now I hand over to our principal, Dr. Jochin Joseph, to address the gathering. Thank you.
Thank you, Rani Miss. Good afternoon, dear friends. Our respected invited speaker, Dr. Bincy Susan Jacobs, Vice Principal, HOD Department of Physics, Mrs. Rosemary John, our librarian, Father Tijomon P. Isaac, NAC Coordinator, and IQC Coordinator of this program, Mrs. Rani George, teachers, students, and my dear participants. Research and Postgraduate Department of Physics and IQC of our college are jointly organizing an international webinar on physical properties of chromium, rhenium, vanadium alloy system. Let me introduce our college to the new participants. Our college, St. Aloysius College, Edatwa, founded in 1965, is managed and owned by St. George Foreign Church, Edatwa, in Kuttanad Taluk, a waterlogged area, a place below sea level in the lake city of Alappuzha. The college is a well-established NAC re-accredited A-grade college offering 9 UG, 5 PG and 2 PhD programs. The college is associated with the DST FIST, RUSA funding, and affiliated to Mahatma Gandhi University, Kottayam. We also have a well-built 50-meter 8-lane swimming pool. The total student strength is around 1100. I congratulate the Department of Physics for organizing the second international webinar in this academic year, especially the HOD Rosemary John and the coordinator Rani George and the joint coordinator Indu Trisa Jochin and the teachers of the Department of Physics. Today we have with us an young, energetic, enthusiastic, vibrant, budding scientist, Dr. Bincy Susan Jacobs, lecturer in the University of Johannesburg, South Africa, for giving a talk in condensed matter field. The topic is physical properties of chromium, rhenium, vanadium alloy system. I am sure that the resource person will take you to the field of low temperature alloy system. I wish all the best for the successful conduct of this international webinar, and I invite the resource person, Dr. BINCY Susan Jacobs, my loving young cousin sister, to start the webinar. Thank you. Over to you, Dr. BINCY Susan Jacobs.
Thank you very much. Thank you for that wonderful introduction. Good afternoon, everybody. Are my slides visible?
Yes.
Okay, thank you. So today I will be taking you through the physical properties of the chromium, rhenium, vanadium alloy system. I present here a part of my PhD work. Okay. So what you see here on the left is the main campus of the University of Johannesburg, which is in Johannesburg, which is the provincial capital of Gauteng, which is one of the 9 provinces of South Africa. The University of Johannesburg came into existence in the year 2005 by the merging of 3 well-established universities, the oldest of which was the Rand Afrikaans University, which was established in the year 1967. The University of Johannesburg is spread over 4 campuses, and we have about 50,000 students, 3,000 of which are international students. University of Johannesburg also, we shortened as UJ. The logo of UJ shows 2 birds embracing an open book, which signifies the joining of the various institutions to become one academic university, one academic entity. The vision of UJ is to be an international university of choice, anchored in Africa, dynamically shaping the future. Okay, so let's get acquainted with the elements of our system. We have chromium, which is the main element that we'll be discussing, vanadium and rhenium. So they are all transition metals. Okay, but the star of the show is chromium. Chromium, let's look at chromium. It crystallizes in the body-centered cubic structure. Its electronic configuration is argon 3d5-4s1. The electron to atom ratio of chromium is 6. It is an antiferromagnet below 312 Kelvin, and it's a paramagnet above 312 Kelvin. Now, the antiferromagnetism in chromium is established by the formation of a spin density wave. I will explain this shortly. Bulk chromium is an itinerant electron antiferromagnetic material that forms an incommensurate spin density wave, which we abbreviate as ISDW, below the Néel temperature 312 Kelvin. Once again, I will explain what this is shortly. And in the formation of the spin density wave, the Fermi surface of chromium has a very important role to play. Okay. So on the left, we have the 3-dimensional representation of the Fermi surface of paramagnetic chromium in reciprocal space. Okay, so the solid and dotted lines represent the boundaries of the first Brillouin zone. We have electron octahedra or electron jack and hole octahedra, which are centered at gamma and eta points in momentum K space or reciprocal space. We also have other features on this Fermi surface, like electron knobs and hole ellipsoids, but these do not partake in the spin density wave formation. On the right, we have the cross-section of the Fermi surface in the 100 plane. Again, the dark line represents the boundary of the first Brillouin zone, and the dotted lines represent the translation vectors for the hole and electron octahedra. Okay, so what happens is, for the formation of spin density wave, a process called nesting occurs. So in pure chromium, the electron sheet is slightly smaller than the hole sheet. Okay, and in the process of nesting, the electron sheet is translated onto the hole sheet through a translation vector Q, the magnitude of which is given by that 2 pi over a 1 plus or minus delta 0, 0, and it is in K space. So this Q represents the distance between the electron and hole sheets in reciprocal space. Here, the delta is what we call the incommensurability parameter, and it arises due to the size mismatch between the electron sheet and the hole sheet. So in order to reduce delta, we have to dope with elements that are electron donors so as to increase the size of the electron sheet. Okay, so nesting leads to spin density wave formation. What happens is the electron sheet is translated onto the hole sheet, and as a result of that, there is Coulombic interaction between the electrons on holes, and parts of the Fermi surface are annihilated as a result of that. What happens then once the spin density wave is formed? So here we have the one-dimensional energy dispersion curve in reciprocal space or K space. We have energy gaps at the edges, the boundaries of the Brillouin zones. So once the spin density wave is formed, you're introducing an additional magnetic periodicity into the lattice. So as a result, you have an additional energy gap 2 delta that is introduced into the system. As a result of that, the energy of the occupied states is lowered and the energy of the unoccupied states is increased. So there is a decrease in the density of states at the Fermi level, and the energy of the occupied states is lowered, and the spin density wave is thus stabilized. Okay, so once the spin density wave is formed, like I mentioned, you have Coulombic interaction between electrons and holes. As a result, you have a reduction in the number of charge carriers. So as you move from the paramagnetic region, you cool down, and as you approach the near temperature, which is about 312 Kelvin, you have the nesting taking place, the recombination taking place, the reduction in the charge carriers taking place, and as a result, you will encounter a sudden increase in the resistivity. And where that occurs, the temperature at which that occurs will then be your transition temperature. So the formation of the spin density wave manifests in the physical properties of the alloys. The dotted line shows the trend if the curve were to remain paramagnetic down to the lowest temperature. Okay, so we keep saying spin density wave. What is it actually? It is just the modulation of the local spin density vector. Okay, so it is an antiferromagnet. So we have the moments at the corner of the lattice are parallel to each other, but anti-parallel to the moments at the center of the crystal. And now in a regular antiferromagnet, you would have the moment magnitudes equal throughout the lattice. Whereas in the spin density wave case, you have the modulation of the moments, magnitude of the moment. So you have a sinusoidal variation. The metal is engulfed by quantum fluctuations. The physics is different, and there's a lot of change that happens in the system. Now, although this transition occurs at absolute zero, we can see effects of it at higher temperatures. So at about 2 Kelvin, we can see effects of it. And this was a groundbreaking study reported by Ye in the year 2002, like I said, that you can drive chromium to a quantum critical point by substituting with vanadium. Okay, so how do we know if we have a quantum phase transition? So we have certain signatures associated with it. We can see the number of carriers drops as you go into the ordered state, as well as the magnetic susceptibility. This is because of the reduction in the density of states at the Fermi level. Okay, so here we have chromium vanadium bulk, alloys. The resistivity, on the other hand, it transitions smoothly through the quantum critical point. But if you look at the low temperature dependence of resistivity on the cube of temperature, you see that the dependence is independent of the dopant concentration. Okay, so it's all straight line dependence. So this was for bulk chromium vanadium alloys, and the tuning parameter here was doping with vanadium. On the right, we have again a chromium vanadium single crystal. Now the vanadium concentration is kept constant at about 3.2 atomic percent vanadium, and here pressure was used as a tuning parameter. Here we can see how the normalized resistivity varies, as well as the inverse Hall or the charge carriers, again a sudden drop upon entering the ordered state. So these are some of the signatures we can look out for to see if our system undergoes a quantum phase transition. Okay, so why did we even begin this study? Well, we wanted to see if we can drive our system to quantum criticality, because quantum criticality was reported in chrome vanadium samples, as well as in 2002, as well as chromium ruthenium vanadium samples in the year 2009. Then we wanted to see if there is superconductivity in our system, because chromium rhenium binary alloys were reported to exhibit superconductivity. And thirdly, we wanted to see if the superconductivity coexists with antiferromagnetism. So basically, we wanted to see if we can develop a phase diagram like this, where you have the classical critical state going into the quantum critical state at the quantum critical point, and then it terminating in a superconducting dome. So this is what we wanted to see if it exists in our system. So here you can see superconductivity coexists with magnetism. So we wanted to see this for the chrome rhenium vanadium alloy system. Okay, so the experimental techniques, our bulk alloys were arc melted in pure argon atmosphere. We then annealed it at 1300 Kelvin for 7 days to improve homogeneity, as well as to relieve the stresses that were introduced during arc melting. Then to check our structure, the quality of our samples, we did microprobe analysis to check for elemental concentration, SEM analysis to check for morphology, and X-ray diffraction for structural analysis. Then, depending on the measurement we are going to do, we need to plane and shape the samples. So for that, spark erosion technique was used to cut and plane and shape the samples into appropriate shapes. Okay, so now what are the appropriate shapes? So we start off with an alloy button like that, and then we use spark erosion and cut the edges and all of that. And then for resistivity measurements are based on Ohm's law, and you need a uniform electric field across the sample. You also need a uniform cross-sectional area and a length which is much greater than the cross-section area. So the ideal shape would be a rectangular bar. And this is the same shape that we use for thermal transport measurements, where you have a temperature gradient across the sample, which gives a voltage, the Seebeck effect. So for electrical resistivity and thermal transport measurements, we use a rectangular bar. Now, for specific heat measurements, what we do is we apply a heat pulse and we allow the sample to relax, and then we do the measurement. So you don't want a sample that is too big, because then the relaxation will take too long. Also, you want the sample to have good contact with the platform. So the ideal shape for a specific heat measurement would be a cube of side 1 millimeter. Magnetization and magnetic susceptibility measurements, the samples are loaded in a straw, so you would have a circular cross-section. Moreover, you want the uniform distribution of moments about the central axis. Therefore, the ideal shape would be a disc of about 2 to 3 millimeter thickness and 5 millimeter diameter. For Hall effect measurements, by trial and error, we found that the best Hall effect measurement was for a sample with thickness 0.4 millimeter, and the length to breadth ratio is 3:2. So you would have typical Hall sample 18 by 6 by 1 cubic millimeter. So that's how, those are the different shapes we use for the measurements. Okay, so once we've got the appropriate shapes, then we measured our physical properties on the quantum design PPMS, which is in UJ in the Department of Physics. We measured resistivity, Seebeck coefficient, specific heat, and Hall measurements as a function of temperature. We also have the quantum design MPMS, which we use to measure magnetic susceptibility as a function of temperature. And the measurements were furthered at another company called Sasol, as well as in Brazil. And we also had to do neutron diffraction. Left over after nesting. So a lot of information can be gathered from this equation. So this black line over here is a fit of this equation to the experimental resistivity data. So you can see it fits well in the paramagnetic region, and this would then be the non-magnetic component of the experimental resistivity data. So if you take the difference between the two, where the difference goes to 0, that would then be your Tn. So that's what is shown in the next curve over here, delta rho. Delta rho is the difference between the experimental resistivity curve and its non-magnetic component. And where that goes to 0, that point is taken as Tn. So those are the three methods in which we can determine Tn from electrical resistivity measurements. Now, when we wanted to see if our system can be driven to quantum criticality, one of the signatures we saw earlier, just to refresh your memory, was that at low temperature, the T-cube dependence of rho was straight line dependences. Now, in our systems, I've just shown representative samples over here with 0, 2.4, and 5.7. We do have a straight line dependence on T-cubed at low temperatures. And we also see that the way in which it depends, so that the rho dependence on T cubed is independent of the concentration. So regardless of what the concentration is, you still have a straight line dependence. Okay, so we constructed a phase diagram from our electrical resistivity measurements. So this red curve over here is a power law fit of this form given there. and we saw the critical concentration was 10.47, very close to 10.5. So antiferromagnetism is suppressed, and the transition is suppressed to 0 Kelvin at about 10.5 atomic percent vanadium. The pink triangles are Tn from the minimum point in the resistivity curve, and the green circles are from CHIU fit. We can see there's very good agreement between the two values. Now over here, we see an inflection or a change in slope over here corresponding to close to 4 atomic percent vanadium. Now we speculated that this could be the transition from the commensurate spin density wave phase to the incommensurate spin density wave phase. It makes sense because over here you have no vanadium. And like I said earlier, vanadium is electron deficient. So what happens is as you add more vanadium, you're decreasing the size of the electron sheet even further, which means you're pushing the system towards incommensurability. So there's a good chance that this bend in the curve corresponds to a commensurate to incommensurate spin density wave transition. We can also get other information. So if you look at the residual resistivity and the magnetic contribution to resistivity. So residual resistivity is just resistivity at the lowest temperature. In this measurement, it was 2 Kelvin. If you look at the trend, you will see it increases up to about 6.9 and then sharply decreases through the critical concentration and remains flat in the paramagnetic region. And the ratio of the magnetic contribution to resistivity to the residual resistivity, same trend, again increases up to about 6.9, close to 7, and then drops sharply through the critical concentration and remains flat in the paramagnetic region. So this dotted line over here is the trend of the curve if it were to remain paramagnetic for all concentrations. It's a fit. The solid red lines are just guides to the eye. Okay, the next measurement that we usually do is magnetic susceptibility measurements. So here we can see a change of slope happening at Tn, and this Tn then corresponds very well with the Tn that we determined from electrical resistivity measurements. So in all these curves, I've only shown representative samples again. So in all these curves, we see a deep valley as well as an upturn at low temperatures. And this has been reported to be a Curie tail, which arises from oxide impurities. And it makes sense because chromium has a high affinity for oxygen. So there is a good chance that our system also has an oxide. So then we thought, okay, so that means this second change of slope, which is similar to the antiferromagnetic transition, should then correspond to the oxide transition. And chromium oxide, Cr2O3, is antiferromagnetic. So we concluded that this then corresponds to the oxide transition. Now, if you look here the temperature for 5.7 atomic percent vanadium, the temperature is about, let's say, close to 150. Whereas for the 6.9 atomic percent vanadium, we see that the temperature is suppressed. It's below 150. So we suggested that this means that it's not just Cr2O3, but rather a vanadium-doped oxide of chromium. Next physical property is Seebeck coefficient, or thermal transport measurement, from which we extract Seebeck coefficient. Now you can see here the anomalies are enhanced compared to electrical resistivity measurements. So you have a dome associated with the transition temperature, and this dome is suppressed and shifted to lower temperatures as you increase the vanadium concentration. Okay, and here to locate Tn, we took the point at which the broken line in the antiferromagnetic region coincides or intersects the broken line from the paramagnetic region, where the two lines intersect. We took that as Tn. And once again, there is good correspondence between Tn obtained from Seebeck coefficient measurements with electrical resistivity as well as magnetic susceptibility measurements. Okay, so if we look at the gradient of the Seebeck coefficient at low temperature, we get a trend like this. Once again, from 0, it drops sharply to past 4%, and then there's a sharp increase and steady decrease through the critical concentration and tending to flatten off in the paramagnetic region. So definitely there is something happening here, which we saw in the phase diagram as well. There is something else happening here. So this anomaly we can associate it with quantum criticality, but as this one, we still needed to investigate further. Now we compare our work with other work with similar diluents. So the red open circles are a contribution from this work. So here we have a log-log plot of the transition temperature as a function of critical concentration or concentration. So if log-log plots are straight line, we know, then it means that we can fit a power law through it. Okay, and the slopes of these lines are the critical exponents. Now we can see our value is 0.53. There's good correspondence with other reported work of quantum critical behavior, of alloys with quantum critical behavior. Over here, again, we have the Tn as a function of vanadium concentration phase diagram. The red curve is our contribution. Again, there is very close comparison with other alloy systems. Now, in the chrome iridium vanadium alloy system, again, we can see the same thing, a sort of inflection, a sort of change of slope before going quantum critical. Hall coefficient, this is one of the most difficult measurements to do. Sample preparation is difficult, as well as the measurement is difficult, and understanding the measurement is also quite difficult. Nonetheless, we did do it. And here we have the Hall coefficient. The black dots are the Hall coefficient data. We can see that for the 0 and the 12.4 atomic percent alloy, the Hall coefficient is negative. Whereas for all other alloys, it is positive, meaning the Fermi surface has predominantly hole-like morphology. So when there was no vanadium, it was negative. Now, upon adding vanadium, because vanadium is electron deficient, it compensated for the additional negative charge carriers, and then therefore the RH became positive. Now, if you remember, this is also a signature for quantum criticality. So our quantum critical point is here, 10.4, and the Hall coefficient should decrease rapidly as it enters the ordered state, and we can see the same thing happening over here. We also see a very deep minimum at about 12.4 atomic percent vanadium. This could be because of the reconstruction of the Fermi surface close to the critical concentration, which is about 10.4 atomic percent vanadium. We are not sure about why this is here. We need to investigate this further. We measured this couple of times and we still got the same value. So this is a correct point, but we're not quite sure what's happening here. We need to investigate it further. Specific heat, we don't see transitions in CP as a function of T. Chrome alloys don't show a transition for specific heat as a function of temperature, but there's still a lot of information we can gather from the low temperature specific heat measurements. So the dependence of specific heat on temperature is governed by this equation. So which means if you plot Cp over T versus T squared, then the intercept would give you the value of gamma, okay, and the slope would be beta. So gamma is the Sommerfeld coefficient. So the insets over here show the low temperature Cp over T versus T squared data for representative samples. Again, we fit a straight line and the intercept gives us the value of the Sommerfeld coefficient, gamma. Now, if you plot gamma that we got from specific heat as a function of concentration, once again, we see something deep, a deep minimum here, followed by an increase and a sharp decrease through the critical concentration, and hopefully it will flatten off. We need more samples to ensure that it is flattening off. So because we keep seeing this, we decided we need to investigate this further. And if you remember the Seebeck coefficient curve, it's very similar. The trends are very similar. You can see the deep minimum. So we decided we need to investigate this further to understand what is happening. And that's why we went to do neutron diffraction measurements. Now, neutron diffraction, neutrons, even though they have no charge, they do have a magnetic moment, which means they can experience a force in a magnetic field, which is set up by unpaired electrons. and as a result, they are scattered from the nucleus. So in neutron diffraction measurements, what we do is we have a collimated beam of neutrons bombarding your samples, and the scattered neutrons are then detected, and the energy of those neutrons are then calculated to give you information about your sample. So for neutron diffraction measurements, we made 4 samples. Now we chose 0% vanadium, 4.2% vanadium, 5.5% vanadium, and 6.2. Why did we choose specifically these 4 concentrations? Well, if you remember the curve that I just showed you, we want to know what's happening here. So we chose one sample there with 0, 4.2, 5.5, and 6.2. So in the vicinity of this minima, we made 4 samples in the vicinity of this minima to investigate what exactly is happening in this curve. So structurally, they are good. We can see 4 BCC peaks. The red curve is our experimental data. The blue are the Rietveld refinement fits. And we see only the 4 BCC peaks of chromium. Okay, and then electrical resistivity, as expected, as you increase the vanadium concentration, again, you suppress the transition. You can see for 4.2, it is there. For 5.5, and then 6.2, it's the lowest. So TN is suppressed as expected. This is the neutron diffraction pattern for the X equals 0 alloy. We see the main 100 magnetic peak, which is suppressed as expected as temperature increases. So as you go from 20 Kelvin to 590 Kelvin, the size of this peak decreases and magnetization is suppressed at 590 Kelvin. So this is the main 100 magnetic peak. We don't see any satellite peaks. And if you just see the main 100 peak or the main magnetic peak, it suggests that your alloy is commensurate. So this X equals 0 alloy is in the commensurate spin density wave phase. Now, in addition to this peak, we see another peak at about 38 degrees. And when we did Rietveld refinement, we saw that it is actually chromium oxide. So now the presence of chromium oxide is confirmed in our system. So Cr2O3, this peak corresponds to Cr2O3, but it is present in very small quantities at about 1.2 weight% in all the alloys, but it is there. Okay, and we can extract other parameters from refinement. Okay, and from neutron diffraction, you can also determine Tn. So you have your magnetic peak, which you saw, and the area below that peak is what we call the integrated intensity. So how do we determine Tn? Well, you have to fit a curve on that peak, find the area below the peak, and where that area goes to 0. So when the peak disappears, then that is your transition. So which means the area should go to 0. So the temperature at which the integrated intensity goes to 0, that is your Tn. Now, because we have 2 magnetic peaks, one belonging to the chromium oxide phase, we also did the integrated intensity for that to find TO, which is the transition temperature of the oxide. Okay, so that was for the alloy with no vanadium. Now, when we add vanadium, so 4.2% alloy, once again, we see the magnetic peak, the 100 magnetic peak, which is suppressed as temperature is increased. Now, in addition to the magnetic peak, we see 2 satellite peaks, which are symmetrically displaced about the main magnetic peak. Now, vanadium is a very poor scatterer of neutrons, unfortunately. So these peaks are barely distinguishable above the background, but they are there and they appear at the calculated positions. So therefore, we believe that this system has got satellites and it's the incommensurate phase. Now, even in the 4.2 alloy, the chrome oxide peak is still present. So therefore, what can we conclude? For 0, it was commensurate. There was only the single peak. But when you added vanadium, you see 2 satellite peaks, which means it goes incommensurate. I'm just going to show you some, because of time constraints, I'm just going to show you some of the other graphs. So here we have again Tn of the 4.2 sample, the same way integrated intensity where it goes to 0. Also for the oxide where it flattens out. And also for the 6.2 sample. Okay, so if we have a phase diagram of the alloy as well as the oxide, so the reds or the brown stars are transition temperature from the saddle point. The pink circles are from neutron diffraction. There's fairly good correspondence for the mother alloy and good correspondence for the other alloys. And also the oxide temperature here again we see as the vanadium is added, the temperature is suppressed, or as in vanadium concentration increases, the Tn of the oxide decreases. So once again, we want to suggest that it's not just Cr2O3, but rather a vanadium doped Cr2O3. This is the last measurement that I would like to share, or the last result. So because the 10.4 alloy is very close to the quantum critical point, which we saw was 10.5, we can push this to quantum criticality using magnetic field as a tuning parameter. So we do see a suppression in Tn up to about 9.5 Tesla. We only measured up to 9.5 Tesla. We need to extend this to see if it actually does suppress to 0. But we also saw some superconducting tendencies in this alloy. So here we have the resistance as a function of temperature for the 10.4 alloy for the different fields. And the inset shows resistance as a function of field at very low temperature. So this is at 375 millikelvin. And there appears to be an upper critical field of 1.8 Tesla. So we published these results. We did publish these results. But we made more samples in this vicinity, but we could not even down to these very low temperatures. So what we think is what's happening in this alloy is they may have been a binary chromium-rhenium cluster, which became superconducting, and it's not the entire alloy that is superconducting. So the conclusion from this work is in the chrome-rhenium-vanadium alloy system, we saw that there is a critical point at about 10.5 atomic percent vanadium. The minimum in the Sommerfeld coefficient curve corresponds to the transition from the commensurate to the incommensurate spin density wave phase. Superconducting tendency was observed in the 10.4 alloy below 1 Kelvin, but we could not observe it in other alloys close to this concentration. So we need to make more binary chromium-rhenium alloys to see what is the exact temperature at which it goes superconducting. So the sample should be structurally good and go superconducting. We can also extend it to single crystals and thin films to see what is the effect of dimensionality. Single crystals will obviously be better samples, more homogeneous samples. So we need to do all of that as part of the future work. I would like to showcase the Department of Physics at UJ a little bit. So these are the various research areas: astrophysics, atmospheric physics, nuclear, theoretical physics, education, and we have a very strong component of condensed matter physics. We have the only angle-to-solid photoemission spectroscopy on African soil. We have the PPMS, MPMS, you've seen that in my slides. And these are the different areas where we have work. We have high-pressure work as well, and F-electron magnetism, quantum criticality, highly correlated matter, all of that. For further information, please visit our website, UJ Physics. This is the Chromium Research Group at the University of Johannesburg. The group leaders are Professor Prinsloo and Professor Shepherd. Dr. Mohanty is the nano expert. He is from Odisha. We have Dr. Ncube. She is a postdoctoral fellow. She is from Zimbabwe. We have Mariam Jacob. She is from Kerala. She is currently busy with her PhD. And we have 3 South African gentlemen. Mr. Nkosi busy with his PhD. Mr. Mulibana and Mr. Sibanda are honors students. The Chromium Research Group has got the cryogenic system. It is a recent acquisition. We can measure physical properties down to 350 millikelvin and up to 14 Tesla. We have very well established labs in the department. We work with bulk, micro, and nano samples. We have equipment for sample preparation, treatment, and characterization. So if your research interests align with this, or if you would like to use any of our lab facilities, kindly contact me at sjacobs@uj.ac.za. I would like to thank respected Principal, Dr. Jochen Joseph Sir, the Head of the Department of Physics, Mrs. Rosamond John, the coordinators of this webinar, Ms. Rani George and Ms. Indu Teresa Jochen, and all of you for your kind attention. Thank you very much.
Thank you, Dr. Bincy. I think we have some questions in the chat box. Kindly suggest some applications of this material. I have a question.
Okay, so there is no application. It is a fundamental physics study, but you can see we did contribute to the body of knowledge. There was a huge gap from very old physics. There was a huge gap, so we contributed to the body of knowledge. So it's a fundamental study. There is no application yet. Maybe there will be if we extend into the nano or into thin films, which is we still have to do.
Okay, there's another question. Are these materials or families exhibiting similar behavior?
Sorry, I didn't hear that. Are they exhibiting?
Similar behavior?
Oh, you mean with other alloys? With other similar alloys?
I think it's many that.
Yeah, so the trends are the same. If it's quantum critical, the signatures will be the same. It's just the temperature or the concentration at which it happens will be different, but the properties will be similar. Yes.
Okay. Your material, does it have any drastic physical property change in comparison with the chromium, vanadium, or the other alloy system?
Chromium vanadium does not have superconductivity, so that's one thing that we expected. So if I do just chromium rhenium, then yes, it will be very different from chromium vanadium. But remember now we're adding vanadium, so there's some, the effect of vanadium, the effect of rhenium, all of that together should come to play. So if you compare just to chromium vanadium, yes, there is drastic change.
Okay, there's another question from Sonia. Ma'am, can you explain spin split temperature?
Sorry, can you explain?
Spin split temperature.
Spin flip. Oh, okay. Spin flip is as you cool from the Néel temperature down, the spins flip to be parallel to the wave vector. So the wave vector is the direction in which the nesting happens. So initially the spins are perpendicular to that wave vector, but then as you go along, as you cool down to 123 Kelvin, the spins become parallel to that wave vector Q, and that is the spin flip temperature.
Okay, there's another question from Joy Matthew. What is the maximum limit of Y?
Maximum limit? Oh, you mean the vanadium constant? There is no maximum limit. So we made up to 13.5, but then we lose interest after that because after that it is paramagnetic. There's no magnetism there. So you could probably dope further, but we don't, because then we don't see any of the transitions. We don't see any of the properties that we expect to see.
Okay. I think that's all. Can we replace?
Sorry, I didn't hear that.
Hello, Bincy, can you hear me?
Yes, I can hear you now.
Okay. Okay. Can we replace vanadium with another elements in the periodic table? Is there any further future continuation of the work?
Yes, we can. I mean, I doped in the second part of my study, I doped with manganese. So there I saw spin glass behavior. So because of time constraints, I couldn't show it here. So in my study itself, I doped with manganese. So chrome, rhenium, manganese. Another option would be to dope with molybdenum. So chrome, rhenium, molybdenum. So these are the nearest neighbors of chromium on the periodic table. So there's vanadium, manganese, and molybdenum. So the next study would be chromium, rhenium, molybdenum. How does that affect the properties?
So you are continuing the work here?
Yes, I'm continuing with bulk, but I'm also extending into the nano and the thin film regime to see the dimension.
What do you expect? Oh, okay. What do you expect if the dimensions are lowered? I mean, when you go to the thin films and nanostructures?
Well, definitely better structural quality. It's very difficult to get very good samples. So even though I showed you samples, there was a lot of trial and error before we got very good bulk samples. So definitely, I think I'll be able to, the structural homogeneity will be able, we can control it better. Maybe there will be some applications. I'm not sure. I still have to investigate it further.
Okay, I have some doubt. How did you? What was the dimension of the materials? Materials you made, and there was a rectangular shape for Hall effect measurements, for coefficient measurement, and some.
So that was about the thickness was 0.4 millimeter, and the length about I showed it. The ratio of length to breadth should be 1:3. So if you have 6 millimeter, then 18 millimeter breadth.
So you don't have any brittle issues, like it won't break this system.
Chromium is very, very strong. I mean, you use it in tools. Chromium vanadium, you use it in tools. So chromium is a very strong material. So that is not a problem. But when we have very thin samples like Hall samples, if you're not careful, you can break it. But otherwise, no, it's not an issue at all.
Okay. I think I have one last question. Can you compare the PhD programs at Johannesburg with the here in Kerala? How can the students enter the university of a PhD program?
Well, I think you just need to have above 60% for your master's degree, for your MSc. And then we have to look for funding. So there is the BRICS program, where Brazil, Russia, India, China, and South Africa are part of it. So there are BRICS funding opportunities available. So interested students, you can please contact us. We can help you to find funding. And once you find funding, it's just a matter of coming over there and starting your work.
Okay. I think the questions are over.
Thank you.
Okay, now I invite our HOD, Mrs. Rosamond John, to give the word of thanks.
A very good afternoon to you all.
Thank you.
Today, I'm very glad to propose vote of thanks to one and all after the successful conduct of this international webinar. First and foremost, let us thank God Almighty for showering all His choices blessings upon us. We express our sincere gratitude to the resource person, Dr. BINCY Susan Jacobs, who is a postdoctoral fellow at the Department of Physics, South Africa. Dr. BINCY Susan is a close relative of our principal, Dr. Joachim Joseph, and she is very dear to our department and our college. Thank you, Dr. BINCY, for sparing your valuable time with us and for giving such an informative presentation on physical properties of chromium, rhenium, vanadium alloy system. Let me express our deep sense of gratitude to all the respected participants, students, and research scholars, faculty members from various parts of our country for sharing your time and participating in this webinar. I would like to thank our most dynamic principal, Dr. Joachim Joseph, for motivating us constantly. Our Vice Principal, Professor Cr84Re16 Joseph, Accuracy Coordinator, Dr. Jubin Anthony, our UGC Librarian, Reverend Father Chijomon P. Isaac, for helping us with all the technical support. Let me thank Ms. Rani George, Coordinator of this webinar, all the fellow teachers of our department, and all our Aloysian family members for their selfless effort to make this event a grand success. Once again, on behalf of Research and Postgraduate Department of Physics, I would like to thank all those who have contributed in one way or other to make this a reality. Thank you. One more request. The link for feedback is given in the dialog box. Please fill it and send. If you will surely get a participation certificate. Thank you.
Thank you very much. Thank you very much.
Okay, thank you, Rosamond. I think I come to the end of the session. Thank you, BINCY, for the session. I think we can wind up.
Thank you very much.